Advanced Molecular Structures, Part 1. In this presentation, we will expand our knowledge of molecular geometry by discussing what we call the expanded octet structures, the structures containing 5 and 6 electron domains. We will finish the presentation by talking about molecular polarity. Here is a summary of all the structures that we will look at in this presentation. We're dealing now with 5 electron pair and 6 electron pair domains around the central atom. 5 electron pairs gives rise to the trigonal bipyramidal structure, and as you can see here, we have a total of 5 molecular geometries that are derived from this basic electron domain geometry. With 6 electron pairs, that gives rise to the octahedral structure, and we're only going to look at a total of 3 molecular geometries, as you can see here. In order to understand how a 5 electron domain structure is put together, it's best if you see the 5th domain as being added at the south pole of a tetrahedron. So the tetrahedron being composed of course 4 other atoms, or let's say electron domains, on the surface of a sphere, with the red atom being at the center, being the central atom. And now we're adding the 5th electron domain at the bottom of the sphere and pushing up those lower electron domains back up to the equatorial axis, and therefore deriving from that what we call a trigonal bipyramidal structure. Let's take a look now at the basic trigonal bipyramidal structure, which we classify as AX5. That's our shorthand for saying A, one central atom, X5, 5 outer atoms, no lone pairs, because if there was a lone pair, that would be represented with the letter E. So obviously then there are 5 atoms around the central atom, there are no lone pairs, and the basic electron domain geometry is known as trigonal bipyramidal, and the molecular geometry in this case is also known by the same name. But of course at this point we have to indicate the angles, and of course when dealing with a molecule we'd also have to show all the atoms involved and the types of bonds involved. Now as you can see here, the angle between the X and the y-axis is 90. The angle at the equatorial plane is 120 between the bonds, and then of course the angle between the upper part of the x-axis and the lower part of x-axis is 180. So let's take a look now at an example of trigonal bipyramidal structure. Are the structures that are constructed by phosphorus, pentafluoride, and oxygen monosulfur tetrafluoride. As you can see here, the first structure on the left fits the molecular geometry in terms of angles perfectly, whereas the structure on the right that has a oxygen double bonded to sulfur, the double bond being of course a larger cloud, will repel the single bonds at the equatorial plane somewhat and shrink the angle between the 2 fluorine bonds down to 112.8 from 120. Now in order to derive the structures, you have to understand that you have to first write the Lewis structure. First you have to write the Lewis structure in order to derive these. Okay, you cannot just look at the formula and just just come up from that with the molecular geometry. Cannot do that. Seesaw is the first molecular geometry that includes a lone pair. Therefore, of course, the number of atoms at the central atom, bonded to the central atom, is 4, one lone pair. The basic electron domain geometry name doesn't change, but its molecular geometry now does change in that we have a lone pair at the equatorial plane, causing the angles between the x and y-axis bonds to be a little bit less than 90, and the angle between the bonds at the equatorial plane to be a little bit less than 120, given that the lone pair is, as you know, a larger cloud, and it repels the bonding pairs a little more strongly. We call the structure, besides seesaw, also distorted tetrahedron or dysphenoidal. And sulfur tetrafluoride is an example of this structure, in that it has a lone pair at the equatorial plane. And as you can see, that lone pair does push the bonding pairs between the sulfur and the fluorine inward somewhat, reducing the angle from 120 to 101.6. The structure that has 2 electron pairs at the central atom is now known as T-shaped, and it has 2 lone pairs at the equatorial plane, causing the bonding pairs between the x and y axis to be at an angle that is a little bit less than 90. The example for T-shaped is chlorine trifluoride. Again, as you can see from this structure, the angle between the fluorine in the vertical plane and equatorial plane are it's close to 90, but it's somewhat less than that, simply because those 2 lone pairs are pushing the bonding pairs somewhat away from themselves, a little more effectively than, of course, another bonding pair would. The last trigonal bipyramidal structure that has 3 lone pairs around the central atom is known as linear, because the 3 non-bonding pairs are at the equatorial plane, whereas the bonding pairs are in the vertical axis, and of course the angle between the 2 bonds in the vertical axis is 180, essentially a linear structure. The example of a linear trigonal bipyramidal structure is this ion of iodine with 3 atoms of iodine. And as you can see, the 3 lone pairs are at the equatorial plane, and the 3 iodines are in a line with each other. This table does a very good job of illustrating all the various types of 5 electron domain structures. You can use this as a reference. The 6 electron domain structure is best envisioned by bringing that 6 electron domain in at the equator, pushing the other 3 aside, by keeping them, of course, at the equator at 90-degree angles. So the resulting structure has all 6 electron domains at the corner of an octahedron with 90-degree angles between all of them. Hence the octahedral structure. As you can see here, the first 2 structures that are possible with a 6 electron domain structure is, of course, the basic one with no lone pairs, AX6, 6 atoms bonded to the central atom, no lone pairs, giving rise to what we call the octahedral structure, where everything is, all the bonds are at 90-degree angles to one another. And of course, between the upper and lower part of any of the bonds in the same axis, the angle is 180. Now, the first structure that is possible by replacing one of the atoms with a lone pair is known, as you can see here, as the square pyramidal structure, where all the bonds are at 90 degrees to one another. Here is an example of an octahedral structure, sulfur hexafluoride, where everything is 90-degree angles. And here is an example of a square pyramidal structure, bromine pentafluoride, where we have one lone pair. The last structure that is possible with a 6-electron domain arrangement and 2 lone pairs is known as square planar, where you have 2 lone pairs in the same axis, and the bonding pairs at the equatorial plane are at 90-degree angles from each other. An example of the square planar type of structure is xenon tetrafluoride, where you can see here that the angle between the bonding pairs is 90 degrees, of course, at the equatorial plane. This table summarizes the structures that you need to know, which involve 6 electron domains.
Let's now talk about molecular polarity. The polarity of a molecule does differ from that of a bond. Whereas the polarity of a bond is determined by the absolute value of the difference between the electronegativity values of the 2 atoms that are bonded, well, the polarity of the molecule is instead determined by the 3-dimensional structure of that molecule. The important question to ask here with respect to molecular polarity is this: within that molecule, are all the bond dipoles, if they do exist, being counteracted? So, for example, in this case, where the bonds are obviously polar because chlorine is much more electronegative than boron, the molecule ends up being actually nonpolar. Why? Because the pull that the 3 chlorine atoms are exerting on the electrons that are belong to boron, these 3 poles are countermanding each other. Therefore, there's no imbalance of electron density anywhere in the molecule. However, in a molecule such as this one, this molecule is definitely nonpolar, and the polarity of the molecule, as indicated by the red dipole moment, is towards the chlorines. Why? Because the electron pull exerted by bromine is not as strong as that exerted by the 2 chlorine atoms, simply because bromine is not as electronegative as chlorine is. As a shortcut to determining the polarity, which is not infallible, you have to be concerned about a few things, which we will talk about. In general, if the ends of the structure are not the same, the molecule is polar. If the ends of the structure are the same, then the molecule is nonpolar. So, for example, look at the 2 structures here. In the case of the first example, the boron trichloride, the chlorine atoms, the ends of the structure, the extremities of the structure are the same, and as you can see, the molecule is nonpolar. Whereas in the other case, the other example, the bromine is a different extremity than the chlorines are, and guess what? The molecule ends up being polar. So let's look at some examples. Hydrogen. Is hydrogen polar or nonpolar? Well, hydrogen is definitely nonpolar. The ends are the same. The molecule is a bond. So in this case, since the bond is nonpolar, right? The electronegativity of hydrogen is the same, so the difference in electronegativity is zero. Therefore, the bond is polar, the molecule is nonpolar. But what about something like hydrogen monochloride? Well, in this case, the molecule is also the bond, made up by the bond. And in this case, there is a pretty strong, well, large enough anyway, electronegativity difference between hydrogen and chlorine. And since the bond is polar, therefore the molecule is also polar. Now, the way of saying this, the ends are not the same, and therefore it has to be polar. And there is therefore a dipole moment that points towards the chlorine, the more electronegative side of that molecule, that bond. Let's look at ammonia. Is ammonia polar? Yes or no? What do you think? Well, look at the dipole moments. Notice that the three nitrogen hydrogen dipole moments point towards the nitrogen because it's more electronegative. But three-dimensionally speaking, there is no dipole moment at the where the lone pair is that is counteracting the other three. Therefore, the molecule is polar, and the electron-rich side is where the nitrogen is. The electron-poor side of this molecule is where the hydrogens are. Now, the way of saying this, the molecule is polar because the four ends are not the same. What about methane? Well, let me ask you this. Are the bonds polar? I must tell you, some publisher will say slightly polar, some people will say that they are polar. It kind of depends on the electronegativity values that are provided to hydrogen and carbon, and those values sometimes depend on who published the table. But essentially, the carbon-hydrogen bond is nonpolar. Therefore, since the molecule, okay, is made up of nonpolar bonds, there is no way that the molecule can be polar. Another way of saying this, of course, is that the corners of the tetrahedron, the ends, the extremities, are the same. Therefore, the molecule is nonpolar. One thing to look out for in this molecule and in future ones, and this is one of the caveats, is there is no way that the molecule could ever be polar if the bonds are also nonpolar.
For your information, here are some dipole moments measurements in the BIES for several different simple molecules. Let's look now at the polarity of molecule that have an expanded octet. Let's take a look at phosphorus pentachloride. Is this polar or nonpolar? What do you think? Well, the molecule is definitely nonpolar because all the dipole moments are the same for all the bonds, and therefore they're all counteracted. And another way, again, that you could look at this, well, look, both axial and equatorial ends, attachments, ligands, they're all the same. Therefore, this molecule is not polar. What about this molecule? Well, this molecule is definitely polar, because although the equatorial ends are the same, and therefore they cancel, the dipole moments cancel each other out, the two axial ends are not the same, and therefore we have a polar molecule with the polarity or the dipole moment of the molecule pointing towards the axial fluorine.
So let's now look at an expanded octet molecule. What about this one? Is this molecule polar or nonpolar? What do you think? Well, according to the shortcut that I gave you for determining polarity of a molecule, you would have to say, well, the ends are not the same, so it's polar. The truth is, however, that it is nonpolar, because the dipole moments in the equatorial plane cancel each other out, and the equatorial moments in the vertical, the axial plane, also cancel each other out. So this is definitely an exception, a caveat to that shortcut rule that I gave you, where although different atoms are at the extremities, the axial and equatorial positions, the dipole moments do cancel each other out, and therefore the molecule is nonpolar. What about this one? What do you think about this one? Is this one polar or nonpolar? Well, it's definitely polar. In this case, the ends are not the same. The part of the molecule where there is a lone pair definitely has no dipole moment occurring there that counteracts the dipole moment of the other bonds.
We have come to the end of the presentation. If you have any questions, please email me.